All right, so we concluded the last lecture by talking about the relationship between internal and external validity and recognizing that we often will sacrifice one in favor of the other. And that's one of the main decisions that researchers have to make. It's part of the planning process is to decide what threats you're willing to accept and how much of each are you willing to basically accept. All right, so the next type of validity is statistical conclusion validity, and this is the probability that the observed relationship or difference in the sample is true in the population. Like I said, this has a lot to do with type 1 and type 2 errors, right? The degree to which we either assume, we reject the null hypothesis when it is in fact false, so we believe that there's a true effect. We found a true effect and we believe it's true for the population, but in fact we are making a wrong conclusion, or conversely, we fail to find an effect and we accept the null hypothesis when in fact a true effect actually does exist. And so that's what statistically, so there's, seems like they're similar between this and external validity, but external validity is more about similarity between our sample and our population and our setting and the setting in which the behavior occurs, whereas statistical conclusion validity really has more to do with alpha levels, right? Probability that we're making a type 1 or a type 2 error. So factors that increase statistical conclusion validity is sample sizes. So we are less likely to make a type 1 error. We're less likely to make a type 2 error, accepting the null hypothesis when it is in fact false if we have an adequate sample size. On the other hand, if our sample size is way too large, we can actually make a type 1 error, right? So a large enough sample, we can find an association between hair color and IQ when it doesn't truly exist because our sample size is so large that it suggests that that's a true effect, right? So we have to find that sweet spot between a sample that's not too small and not too big. Another thing is a homogeneous sample. We're much better able to see differences between groups that are due to our independent variable when our sample is very similar in the beginning, right? So especially if our independent variable does have an effect, then we're much more likely to be able to see it when our sample is homogeneous, excuse me. Another thing is having measures that are reliable and valid. Measures that are low in reliability and validity, in fact, reduce statistical conclusion validity. There's some other factors that take into consideration. We see something called shared method variance, and this is the idea that when you're using the same type of measurement for all of your variables, people have a tendency to respond to things like questionnaires in the same way. And so if you get a person who is hyperbolic, they may answer on the extreme ends, both pre and post test, whereas you get somebody who's more middle of the road, they might answer close to the middle, and they do that both pre-test and post-test. And so the correlations that you might observe from pre-test to post-test or between our two measures say, of risk-taking and alcohol use may be more due to how people respond to questionnaires than due to a true association between those variables, right? And so that's a different issue, but reliable measures, if they're not reliable, then we are not going to be confident that it's our manipulation that's causing changes. It might actually just be the fact that the measure doesn't produce consistent results across time. And the degree of control, right? Standardization of our procedures, reducing the number of extraneous variables or being able to control for extraneous variables also increase statistical conclusion validity. So you can see that a lot of these things overlap with internal validity, and there is in fact a pretty strong association between statistical conclusion validity and internal validity. The things that can reduce statistical conclusion validity would be low power, meaning we don't have a sample size that's large enough to detect effect. And if that's the case, we're likely to make a type 2 error. In fact, type 2 error is considered the power problem, meaning there isn't enough power in our sample to find an effect even if it exists. right? And so the idea is that we're going to want to um, adjust, try to increase our sample size to that sweet spot that is optimal, right? Large enough to get an effect, but not so large that we find spurious or uh, effects that just happen randomly, right? So like I said, this can be addressed by increasing the sample size. It can also be addressed by changing our alpha, right? So if we raise our alpha from 0.05 to 0.1, we increase the likelihood of making a type 1 error. We'll find an effect if it's there, but of course we also increase the risk of making a type 1 error. If we reduce alpha and we say, okay, instead we want to go from 0.05 to 0.1, we increase the likelihood that we're going to be making a type 2 error, but we decrease the likelihood of making a type 1 error. And these are all, again, decisions that researchers have to make. Which type of error are we more willing to accept based on the consequences of making that type of error? As we've talked about, statistical tests have certain assumptions that must be met in order for us to be confident that the results that are produced by those tests actually represent what's happening in the population. And if we violate those assumptions, then even if we find a statistically significant effect, we can't be sure if what we have found is true in the population. So one of the assumptions that's which is pretty much true for all inferential statistics, is that the traits are normally distributed within the population. And in general, most of the traits that we'll be measuring, that's true for. But if it's not, then we might need to use some kind of non-parametric test or another type of test. So if we violate the assumptions, that reduces our confidence in the results of our statistical analysis. The next is the phishing and error rate problems, and I'm going to demonstrate this to you when we talk about analysis of variance. So it's going to be, kind of fleshed out, but suffice to say right now that the more comparisons you make, right, so the more hypotheses that you're testing, the more likely it is that you're going to find effect that is not true. The more likely it is that you're going to make a type 1 error, meaning that the effect happens simply randomly and not due to any true differences between groups. So this means we need to keep ourselves focused on a few questions. All right. I mean, there is this tendency to want to sort of explore the study the question as comprehensively as possible, but the more comparisons that you do, the more likely it is that you're going to make a type 1 error, right? That you're just going to find a significant effect simply randomly, and we call that a spurious effect, okay? Unreliability of measures. Using measures that are low in reliability also reduce your chances of finding meaningful results. So it's important that when we do this, that we select measures that have been psychometrically evaluated, right? So that they're psychometrically sound, or if we're going to make up our own items, that we then test for the internal reliability of the measures. And then the last is restricted range. This is when most of your participants are scoring close to one end of the scale or another. So an example from some of my research, we would assess motivation for treatment among our participants at intake to treatment. Well, regardless of how motivated they are, every participant or every client was going to tell us that they were highly motivated. So all of our scores actually fell at the high end. So when we went to go and actually use those motivation scores to try and predict retention, we actually found the opposite result. We found actually a negative correlation between motivation for treatment and retention, meaning that the more motivated they are, the more likely they were to drop out. And really this was because retention, most patients dropped out after intake, so our retention was really low, and then also most patients reported being highly motivated at treatment, and that produced this effect that really was not a true representation of what was going on in the real world. All right. So trying to get trying to recruit a sample that has a more normal range of scores is going to be important for statistical conclusion validity. All right, the last is construct validity, and I'm not going to talk about this in too much detail. But suffice to say that this gets at the degree to which our independent and dependent measures actually measure the traits or constructs they're intended to measure. And we've talked about internal reliability, we've talked about construct validity, judgment, and empirical validity, things like that. The things that increase construct validity are using measures that have research supporting the reliability and validity, right? So these are studies that have measures that have undergone a rigorous development process and have been evaluated to show that they have test-retest reliability and internal reliability and a high degree of construct validity. Another is that participants are blind to the true purpose of the study, right? So if people figure out our manipulation, or if they know what group they're in, they may change their behavior, and that's going to then change whether or not we can draw meaningful conclusions from our research. And the last is to use as few measures as possible to minimize fatigue or boredom, right? So the longer the measure, the more likely it is that people get bored, the more likely they start to just either get into a response set where they basically give the same answer across all questions, or they start to answer randomly. They draw patterns like in your Scantron forms or something. Threats to internal or construct validity, is our hypothesis guessing, right? So this is when the participant figures out what the experimenter is trying to study and changes their behavior consistent with that understanding. This is problematic when measures are, the measures that we're using have a high degree of face validity. That is, it's obvious what they're measuring. And so one of the things that we sometimes do is add in filler questions that we're not interested in them specifically from an empirical standpoint, but rather they're in there to mislead the participant about what the study is actually getting at. Experimenter expectancies, right? So if the manipulation or data collection involves involvement of the experimenter, then the experimenter can inadvertently influence the way in which participants respond. And I mentioned this earlier, right? That just how the experimenter asks a question can influence how a participant responds. Something like, as I mentioned earlier, so you must be feeling a lot better, to our experimental group that we're expecting to, or our active treatment group, or I'm guessing you're, so how are you feeling? Or, I hope you're not feeling too bad, to our placebo group. The construct is not adequately defined. This is a particular problem if your manipulation is so vague that the participant actually doesn't pick up on it. So sometimes, it might be something like you're varying the gender of the participant in your description, and if the person isn't paying attention to that, then when they answer your dependent measure, we don't know exactly what they're responding to. So it's important that we adequately define the construct. We make sure that we're measuring it comprehensively, and that's really important for our dependent measure. But for our independent measure, we're going to want to do what's called a manipulation check to make sure that participants actually picked up on the manipulation, and so that we are sure that their responses are at least potentially being influenced by their true understanding of what they were reading, as opposed to just, again, random. And then treatment diffusion, and this is unlikely to happen in our online studies, but this is when the treatment diffuses so that there's no difference between the levels of the independent variables. So for example, in the research I did in Baltimore City, we had clinicians doing, in the same clinic, doing the standard treatment, doing role induction, and then doing role induction plus behavioral contracting. And the fact that all three treatments were going on at the same time meant that there could have been diffusion, right? Which is that the standard treatment clinicians picked up on what was going on in the role induction sessions and adopted some of those procedures into their practice. And therefore, that would then mask any potential differences between the groups, because the groups themselves are no longer really different, right? They're doing the same thing. All right, so that is the end of validity.